There is a number that astronomers do not like to say out loud, not because it is classified, not because it belongs to a government agency or sits behind a password-protected server in a university basement. They do not like to say it because every time someone does, the room gets a little quieter, and the people who have spent their careers building models of the universe have to sit with the fact that the number does not fit. It has never fit, and after what was found in the most recent analysis of the object at the center of this story, it fits even less than it did before. You already know the object, or you think you do. TON 618. The ultramassive black hole, 10.5 billion light-years from the planet you are currently standing on. The one that weighs 66 billion times the mass of our Sun, the largest confirmed black hole in the observable universe. You may have read about it, you may have watched a video, you may have come away with a rough mental picture of something enormous and ancient and safely, reassuringly far away. The kind of thing you look at from a very comfortable distance, feel appropriately awed, and then go about the rest of your evening without losing any sleep. That picture just changed. In the last cycle of data released from instruments that did not exist when TON 618 was last seriously studied, something was found in the data surrounding that object. Not inside it. Not in its immediate vicinity. In the broader structure of space around it. Something that forces a reclassification of what TON 618 is, what category of phenomenon it belongs to, and, most disturbingly, what it implies about everything else that shares its class. The revised understanding is not 66 billion times worse in the way you might be hoping for. TON 618 has not tripled in mass overnight. It has not shifted position. It is not heading here. The number that keeps astrophysicists quiet at conferences is not a threat in the way that word normally works. It is worse than a threat in the way that realizing you have been reading a map upside down for the entire trip is worse than just being lost. The map was wrong. Not in one corner. In the foundational assumption about what kind of territory you were crossing. Whether you should be frightened by what was found is the question this script will answer. But not yet. Because to understand what reclassification actually means, and why this particular one lands differently than any data revision that has come before it, you first need to understand what we thought TON 618 was, and then you need to understand what, quietly and without fanfare, it has turned out to be. Something else entirely. Something that changes the question we thought we were asking. Before we get started, if you love exploring the depths of space much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Part 1. The object we thought we understood. Let us go back to the version of TON 618 that existed in our collective knowledge until recently. The version that was already, by any reasonable measure, the most disturbing object in the observable universe. The version we had made our peace with. The version we had, in the specific way that humans make peace with incomprehensible things by giving them names and filing them in categories, convinced ourselves we understood. TON 618 sits at a cosmological redshift of approximately 2.219. That number by itself means almost nothing until you convert it into something a human brain can process. At that redshift, the light arriving in our telescopes tonight left its source when the universe was roughly 3.5 billion years old. The universe is now approximately 13.8 billion years old. That means the light currently registering on our instruments has been travelling for over 10 billion years. It departed before our sun existed, before our planet existed, before any of the atoms currently arranged into the specific configuration called U had been assembled into anything more organized than a diffuse cloud of stellar debris drifting through an arm of a young galaxy. The light left anyway, 10 billion years. Through expanding space, through gravitational lensing events, we will never catalogue past galaxies that formed and burned and merged and died in the time it was travelling, aimed at a patch of sky where one day a technological civilization on a small rocky planet would build instruments sensitive enough to catch the handful of photons that survived the crossing. Most of the photons emitted by TON 618 that were aimed in our general direction did not make it. They were absorbed, they were scattered. They collided with gas clouds and dust grains, and the diffuse intergalactic medium, and were redirected into paths that will never intersect with anything that can receive them. The universe is not efficient. It does not care about messages reaching their destinations. A tiny fraction survived. Those photons are arriving right now, as you read or listen to this. For most of astronomy's engagement with TON 618, those photons told one story. Here is an ultramassive black hole, the single largest gravitational object we have confirmed, feeding voraciously at the center of a distant galaxy, blazing with a light of hundreds of millions of suns of accretion, and completely, entirely, mathematically impossibly large for the age of the universe at the time it formed. That last part was the problem we had already accepted. We had named it, filed it under the heading of things we cannot yet explain, and moved on. The impossibly fast growth was a known anomaly. The 66 billion solar mass measurement was a known anomaly. The quasar was a known anomaly. We had gotten comfortable with it. That comfort was the mistake. Here is what we thought we were looking at, in careful detail, so that the reclassification lands with the weight it deserves. A quasar is what happens when a supermassive or ultramassive black hole is actively feeding. Matter falls toward the event horizon in a spiraling disk, the way water spirals toward a drain, except that the forces involved are so extreme that the material heats to temperatures of millions of degrees before it crosses the point of no return. That superheated disk radiates energy. It radiates so intensely that a single quasar can outshine every star in every galaxy in a given patch of the sky. The radiation from a quasar is not subtle. It is not a signal you might miss. It is the most luminous steady-state phenomenon in the known universe, visible across billions of light years, marking the presence of a feeding black hole the way a lighthouse marks a coast, except no lighthouse ever built could be seen from 1 billion miles away, and the quasar can be seen from 10 billion light years. TON 618's quasar output was estimated at approximately 140 trillion times the luminosity of our Sun, 140 trillion. If you place the entire Milky Way galaxy, all 400 billion stars of it, every red dwarf, every white dwarf, every blue supergiant, every brown dwarf and every stellar remnant and every protostar still condensing out of molecular clouds in the galaxy's star-forming regions, placed all of that next to TON 618 and asked which one was brighter, the answer would not even be a competition. The quasar would win by a factor of several thousand to one. The entire output of a galaxy of 400 billion stars, reduced to a rounding error in the luminosity budget of a single feeding black hole. One object, brighter than thousands of galaxies combined, that was the light signature. Now the mass, 66 billion solar masses. Some revised estimates have placed it closer to 40 billion, and some observational analyses have pushed toward the higher end of the range. For our purposes, the exact figure is less important than developing an intuition for what it means, because human language was not built to carry numbers of that size, and the brain tends to flatten them into equivalents when they are separated by trillions. Try this instead. Our Sun has a mass of approximately 2 times 10 to the 30th kilograms. That is 2 followed by 30 zeros, 66 billion of those, 66 billion suns. If you could somehow transport every star in the Milky Way and pour them, one by one, into the growing mass at TON 618's center, you would fall approximately 165 times short. You would need to drain 165 entire Milky Way galaxies, every star in every one of them, to match the mass measurement of a single object. The event horizon that results from that mass has a radius of approximately 1,300 astronomical units. 1 astronomical unit is the average distance between the Earth and the Sun. It is roughly 93 million miles. Pluto, which most of us grew up thinking of as the farthest thing in our neighborhood, orbits at about 39 astronomical units from our Sun. Neptune orbits at about 30. The event horizon of 618 would extend past where Pluto orbits, and keep going, past 30 Plutos, past 40, out to 1,300 times the Earth-Sun distance, in every direction, in a perfect sphere, below which not even light can climb back out. To cross that event horizon in a ship travelling at the speed of light, which you cannot do because you have mass, but suppose you could, would take approximately 2 weeks. Not 2 weeks of travel inside the black hole, 2 weeks just to travel from one edge of the event horizon to the other. A beam of light, the fastest thing in the universe, requires 2 weeks to traverse a single object. If you tried to visualize that from a hypothetical vantage point, hovering somewhere near the edge of the event horizon, which you could not survive approaching for reasons that will become clear, the visual geometry of space itself would be distorted beyond recognition. Every photon arriving at your eye from any direction would have traveled through severely curved spacetime. The stars you were used to seeing as points of light would be smeared and bent into arcs. The light from galaxies directly behind the black hole would appear in front of you, bent around it by gravitational lensing so extreme that the universe would fold into a single halo of distorted light above you. Below you, where the event horizon sits, there would be nothing. Not darkness the way a cave is dark. Not the darkness of a room with the lights off, where your eyes simply need time to adjust, and the walls and furniture slowly resolve in the ambient glow from a window. A perfect, total, complete absence of any photon reaching your retina from that direction. A black so fundamental that every black you have ever encountered in your life, the darkest paint, the deepest cave, the middle of the ocean at midnight, would look bright by comparison. The event horizon is not a surface that absorbs light. It is the edge of a region where light does not exist as a forward direction. It is, in the most literal physical sense, the end of the observable universe from any point above it. Your watch would tick slower near the event horizon than it would for anyone watching you from a safe distance. Time dilation near an object of this mass is not a theoretical abstraction. It is a physical reality. Time runs slower in stronger gravitational field. Near the event horizon of TON 618, a minute of your subjective experience would correspond to years, then decades, then centuries of elapsed time for observers far away. Drift a little closer, and a single year of your time would encompass the rise and fall of civilizations back on the world you left. You would be watching the universe age around you while barely aging yourself. This is not a metaphor. This is what the equations predict. And everything we have measured about gravity confirms that the equations are correct. That is what we were looking at before the reclassification. An object of incomprehensible mass, a quasar of impossible luminosity, an event horizon large enough to swallow multiple solar systems. Something that should not exist and manifestly does, glowing in our telescopes, sending its ancient light across 10 billion years of expanding space, already posing questions our physics cannot answer. All of that was true, all of it was already established, and all of it was the easy part. Part 2. What reclassification actually means. Before we go any further into what was found, we need to spend a moment with the word reclassification, because it sounds bureaucratic in a way that disguises how significant it actually is. Most people, when they hear that a scientific object has been reclassified, think of Pluto. In 2006, Pluto was reclassified from planet to dwarf planet, and the result was a minor cultural controversy that lasted about 3 years and produced a great many novelty mugs. The impression that reclassification creates is one of administrative adjustment, a filing error. Someone moved a label from one folder to another, and some people got upset about it at conferences, and eventually everyone moved on. That is not what happens when an ultramassive black hole gets reclassified. In physics and astrophysics, an object's classification is not a bureaucratic formality. It is a compressed description of the physical processes that govern that object. Its classification encodes the energy budget it operates within, the feedback mechanisms between the object and its environment, the theoretical framework required to explain its formation, the predictions its existence generates for everything in its vicinity, and the equations that must produce its observed properties when you run them forward from the initial conditions. When an object's classification changes, all of those things change simultaneously. Every equation that was pointed at it has to be repointed. Every model that used its parameters as inputs has to be rerun with the corrected parameters. Every prediction that was generated using the old category needs to be replaced with a new one generated from the new category, and every previously unexplained anomaly in the surrounding region needs to be re-examined through the new lens to see whether it was actually evidence for the new classification all along, sitting in the data, unnoticed, waiting for someone to look with the right instrument. Reclassifying a stellar mass black hole tells you something. Reclassifying a supermassive black hole tells you quite a lot. Reclassifying the largest confirmed object in the observable universe tells you something about the structure of the entire universe, because the largest confirmed object in the observable universe is not just one data point in a catalogue. It is a boundary condition. It defines an edge of what is possible. When what is possible turns out to be different from what we mapped, the entire territory changes. This is not like moving Pluto to a different folder. This is like discovering that the folder system itself was based on a misunderstanding of what folders are for, and here is the specific misunderstanding the reclassification corrected. TON 618 was classified as a solitary quasar, one black hole, one accretion disk, one source of radiation, one gravitational entity at the center of one galaxy, blazing alone in the early universe, eating matter and emitting light at a rate that defied explanation. Singular, extreme, anomalous and singular. The revision changes the word singular. Not because the mass estimate went up, not because a companion galaxy was found orbiting it in some distant sense, not in a trivial or minor way. The revision changes singular because of what appeared in the infrared data surrounding it. Part 3. The instruments and the discovery. To understand what the new data showed, we need to spend time with the instruments that produced it, because the instruments are always part of the story. The history of astronomy is largely the history of building better eyes and then being surprised, sometimes thrilled, sometimes shaken, by what the better eyes find. Every major revolution in our understanding of the cosmos has been preceded by a technical advance, a new capability, a new wavelength range, or a new sensitivity threshold, or a new data processing technique that allowed us to see something that was there all along and that we had simply lacked the tools to extract from the noise. For most of TON 618's history in our awareness, The data we had came from ground-based optical and radio telescopes, supplemented by archival observations from the Hubble Space Telescope. Those instruments told us what we have already described: an ultramassive black hole, a blazing quasar, a host galaxy whose light was largely overwhelmed by the accretion disk, a redshift of approximately 2.219, a mass that could not be explained by any standard formation mechanism, a luminosity that outshone galaxy clusters. That data was extraordinary. It was the data that produced 66 billion solar masses as a figure. It earned TON 618 its place at the top of every list of the universe's most extreme objects. But it was limited in specific ways that matter enormously. The first limitation was spatial resolution. When the light from a source 10 billion light-years away reaches a telescope on the surface of the Earth, it has been travelling through an expanding, gravitationally complex universe for 10 billion years. The signal is extraordinarily faint. The source appears as a point of light, even in powerful instruments. The quasar, that blazing accretion disk, is so bright that it dominates all other information from the surrounding system. The quasar's light drowns out the host galaxy. It drowns out any structure near the quasar. It drowns out anything in the immediate vicinity that is not producing a comparably luminous signal. You see the quasar. Everything else is buried in the glare. The second limitation was wavelength. Optical telescopes see optical light. But the most interesting astrophysics of early galaxy formation, dark matter distribution, cold gas dynamics, the structure of old stellar populations, a great deal of that physics is not written in visible wavelengths. It is written in infrared emission, in millimeter wave observations that cut through dust and reveal mass distributions, in the specific spectral signatures of molecules and dust grains heated by radiation from an active nucleus. Optical observations, however precise, were looking at the universe in one colour and calling it the whole painting. The James Webb Space Telescope changed the second limitation fundamentally. Webb's primary capability is in the near-infrared and mid-infrared portion of the spectrum. This is not an accidental design choice. It is a consequence of the physics of cosmological redshift. Light that was emitted in the ultraviolet at high redshift, the energetic, short-wave radiation that blazing quasars and young stars produce in abundance, has been stretched by the expansion of the universe during its 10 billion-year journey. When it arrives here, it arrives at longer wavelengths. The ultraviolet has been stretched into the optical. The optical has been stretched into the near-infrared. The near-infrared has been stretched into the mid-infrared. Webb was designed to see light in exactly the wavelength bands where the early universe's radiation arrives, which means Webb was designed to see the early universe in a way no previous instrument could come close to matching. Additionally, Webb operates in space, above the Earth's atmosphere, which absorbs much of the infrared radiation that Webb is designed to detect. Ground-based infrared observatories work around this, but only partially and at significant cost to sensitivity. Webb has no atmosphere to contend with. It sits at the L2 Lagrange point, a gravitational equilibrium position 1.5 million kilometers from Earth, where it maintains a stable platform for observations with no atmospheric interference, no day-night cycle, no thermal fluctuation from the Earth's own infrared emission. And when Webb's data on the region of sky containing TON 618 was analysed, when the infrared images and spectra were processed through the pipeline and examined by the teams who had spent months anticipating what the data might contain, something appeared that had not been resolved before: a second source. Not right on top of TON 618, not clearly merged with it or obviously part of the same accretion disk or emission region. Offset by a small but measurable angular separation, small enough that in previous ground-based optical data, it would have been completely buried in the wings of the quasar's point spread function, indistinguishable from the smeared glow of the primary source. But in Webb's infrared data, at the sensitivity and angular resolution Webb achieves in deep field observations, the second source resolved, it separated. It became a distinct object. Its redshift, when measured from its spectral features, matched, not approximately, not within a broad error bar that could be explained by two unrelated objects coincidentally aligned along the same line of sight. The redshift matched TON 618's redshift to within the measurement precision of the instrument, which means the second source is not a background galaxy accidentally positioned behind TON 618 in our view of the sky. It is at the same cosmological distance. It formed at the same cosmic epoch. It is part of the same physical system. There is something else at the redshift of TON 618, something that was not in the catalogue, something that has been sitting there, in that patch of sky, for as long as we have been pointing telescopes at it, invisible behind the glare of the most luminous object in the visible universe, waiting, not with any awareness or intention, but in the patient way that facts wait, for the right instrument, the right wavelength, the right sensitivity, the right eye. The right eye was finally built, and it looked and the second source was there. The question that immediately followed was what the second source is. Part 4. What the second source might be. The discovery of a source at the same redshift as a known quasar raises immediate questions. And the first one is whether the two sources are physically associated or whether the redshift match is a coincidence. Coincidences in astronomy are possible, and this one needs to be evaluated carefully before drawing conclusions. The angular separation between the primary source and the secondary, combined with the shared redshift, was used to calculate the projected physical separation. At TON 618's redshift, the angular scale of the infrared images translates to a projected separation of several tens of thousands of light years, comfortably within the scale of a galaxy or a galaxy group, not so close that the two sources are obviously a single system, and not so far that they are obviously unrelated. The statistical probability of a chance alignment of a completely unrelated source at the same redshift appearing so close in angle to TON 16 on the sky is not zero, but it is small. The density of sources at precisely that redshift in a randomly chosen patch of sky, with the luminosity properties of the secondary source, places the chance alignment probability at well below 1% when the full set of observational constraints is applied. Below 1% is not impossible, but it is unlikely enough that the working hypothesis, the hypothesis that drives the current analysis effort, is that the secondary source and TON 618 are physically associated, that they occupy the same region of space in the early universe, that they are, in the word that changes everything about this story, related. The second question is the nature of the second source. It is not producing a quasar signature as bright as TON 618's primary. It is not blazing at 140 trillion solar luminosities. Its emission is more subdued, fainter in the optical, but detected in the infrared at a level consistent with a large galaxy hosting an active nucleus that is either in a less luminous phase of feeding, or more heavily obscured by dust, or operating at a lower accretion rate, or some combination of all three. All of those possibilities are physically plausible. Black holes go through cycles of activity, and it would not be unusual for a companion at the same redshift to be in a different phase of its accretion history than TON 618 itself. The mass estimate for the second source is more uncertain than TON 618's primary mass, because the secondary's emission is fainter and the constraints are less tight. But the range that comes back from the stellar mass models and the dynamical constraints is not small. The estimates span from roughly 15 billion to 45 billion solar masses for the central black hole. Taking the midpoint of that range, around 30 billion solar masses, the combined mass of the proposed system exceeds 90 billion solar masses. 90 billion solar masses in one system, not spread across a galaxy cluster, not distributed across millions of light years of structure, in what may be a gravitationally bound pair, orbiting a common center of mass, sharing the same dark matter halo, located at the same cosmic epoch in the same vast overdensity of the early universe. If that interpretation is correct, and it is not yet proven but it is not easily dismissed, then what we identified as a single ultramassive black hole and classified as a solitary quasar is a binary system. A pair of ultramassive black holes, the largest known example of a class of object, the supermassive binary, that exists throughout the universe in smaller forms, that produces the gravitational wave background the pulsar timing arrays have now detected, and that, at the scale proposed for this system, represents the most extreme gravitational merger event the universe can produce. Part 5. The scale of the proposed binary. Let us pause on the scale for a moment, because the numbers deserve the same careful treatment we gave to TON 618's primary. TON 618's primary black hole at 66 billion solar masses has an event horizon radius of roughly 1,300 astronomical units. We established that earlier. We walked through the solar system comparisons. We noted that light takes 2 weeks to cross the event horizon diameter. We described the visual geometry that would confront any observer near it. The secondary black hole, at the middle estimate of 30 billion solar masses, would have an event horizon radius of approximately 600 astronomical units. Smaller than the primary, but not by a factor that makes it manageable. 600 astronomical units extends past Pluto 15 times over. If the secondary's event horizon were placed at our Sun, it would extend to roughly twice the orbital distance of Pluto in every direction, swallowing our entire solar system and everything in it, and still having room to spare. Now consider the two of them together, two objects of this scale, sharing a gravitational system, orbiting a center of mass that lies somewhere between them. Their individual event horizons not currently touching. They are separated by some physical distance in the early universe, but both sitting within the same dark matter halo, both feeding from the same reservoir of primordial gas, both blazing with their respective accretion signatures, each one individually the most extreme gravitational object most solar systems will ever interact with. and the two of them linked by gravity into a slow, inexorable billion-year spiral. The orbital dynamics of such a system are governed by general relativity. As the two massive objects orbit each other, they distort the fabric of space-time around them in a time-varying pattern. That time-varying space-time distortion radiates energy. The energy radiates in the form of gravitational waves, ripples propagating outward at the speed of light, carrying information about the orbital motion of the pair, slowly draining energy from the orbit and causing the orbital separation to shrink. The shrinkage is gradual at large separations. The gravitational wave luminosity increases as the separation decreases, and the inspiral accelerates. The final plunge, when the two event horizons approach and merge, occurs over a fraction of the total inspiral time, but releases the bulk of the gravitational wave energy. For a system of this mass, the characteristic frequency of gravitational waves during the inspiral phase falls in the nanohertz range, billionths of a hertz. This is not a frequency that LIGO or Virgo can detect. Those instruments are designed for the kilohertz range of stellar mass black hole mergers, but it is precisely the frequency range that pulsar timing arrays are sensitive to, and it is within the range that the LISA space-based gravitational wave detector, scheduled for launch in the 2030s, is designed to characterize in detail. The total energy release at merger for a system combining 66 billion and 30 billion solar masses would be equivalent to several times the rest mass energy of our Sun, converted entirely into gravitational wave emission in the final moments, not over millions of years. In the final seconds of the merger, as the event horizons touch and the two objects cease to be distinct entities and become one, the power output in gravitational waves would exceed the electromagnetic luminosity of the entire observable universe. Let that land. More energy, emitted in the form of gravitational waves, in the final moments of that merger, than every star in every galaxy in the entire observable universe emits in electromagnetic radiation simultaneously. For a fraction of a second, somewhere in the early universe, at a location we know approximately, the fabric of space-time was more violently disturbed than at any other event since the Big Bang, and the ripples from that disturbance, if it has already occurred, are traveling toward us right now at the speed of light, through everything. They will arrive, or have already arrived, as a very faint, very low frequency stretching and compressing of space around us, undetectable to any human sense, detectable, in principle, by the next generation of instruments, carrying a message from the most energetic event in the post-Big Bang universe. The message will say, two unimaginably massive objects found each other in the early universe and became one. We may be the first generation of humans with the technological proximity to hear it. Part 6. The numbers that should not be possible now. We have to talk about what a system like this means for physics. Not the drama, the physics. Because the physics is where the second level of dread lives. Quieter, colder, and in some ways more profound than anything that has come before. Start with the formation problem. Ton 618 as a single black hole was already impossible. That was established and we accepted it. The argument runs as follows. Black holes grow by accreting matter. The maximum rate at which a black hole can accrete matter is limited by the Eddington limit, the threshold at which the radiation pressure from the heated infalling material pushes back against further infall with exactly the force needed to halt accretion. Grow from a stellar mass seed at the Eddington rate, and you double in mass every several tens of millions of years. Run the clock back from 66 billion solar masses to the Big Bang, and no matter how generously you set your initial conditions, you cannot get to 66 billion solar masses in the approximately 3.5 billion years available between the Big Bang and the epoch when Ton 618's light left its source. The time is too short, the growth is too slow, the object is too large. We accepted this. 3 theories were proposed, none were proven. The universe was building things it should not have been able to build, and Ton 618 was the clearest evidence. We put it in the unexplained folder and moved on. Now consider what a binary system does to that problem. If the second source is real, if there are 2 ultramassive black holes at that location, each independently growing to tens of billions of solar masses within the same insufficient time frame, the formation problem does not simply double, it squares. 2 ultramassive black holes in the same system require 2 impossible growth histories unfolding simultaneously, presumably drawing from the same primordial matter reservoir. They need to have formed within the same dark matter halo, or at least in halos that merged early enough to produce a bound system by the epoch we observe. They need to have each grown independently to supermassive status, or grown together, exchanging mass through interactions, or seeded from the same initial primordial configuration, all within a universe that, according to standard models, should not have had enough time or enough concentrated matter to do any of it once, let alone twice in the same place. And here is where the third formation theory, the primordial black hole hypothesis, becomes substantially more compelling. The primordial black hole hypothesis proposes that some black holes did not form from collapsing stars at all. They formed directly from density fluctuations in the first fractions of a second after the Big Bang, when the universe was hot and dense beyond our ability to directly probe, and matter was not yet organized into atoms, let alone stars or galaxies. In that scenario, the very first structures to form in the cosmos were not stars. They were black holes, ancient, pre-stellar, formed in the chaos of the universe's infancy. Growing from those first moments, long before the first star ignited, accumulating mass in the primordial soup of the early universe. A single primordial black hole, given enough time, enough matter, and enough of the universe's infancy to exploit, could grow to ultramassive scales by the epoch we observe TON 618 at. The formation timeline stops being an insurmountable problem and becomes merely a challenging one. But two primordial black holes, forming from the same overdense region, growing in the same gravitational environment, perhaps seeded by the same extreme density fluctuation that collapsed into two centers of mass rather than one, would require an overdense region in the primordial universe of a scale that our standard inflationary model does not typically produce. It can produce overdense regions. It routinely produces the seeds of all the structure in the universe we observe. But an overdense region extreme enough to seed two black holes that each independently reach tens of billions of solar masses by a universe age of 3.5 billion years, that requires an amplitude of primordial fluctuation at the high end or beyond the distribution that standard inflation predicts, which means that the reclassification of TON 618, if the binary interpretation holds, is not only a problem for models of black hole formation, it is potentially a problem for models of cosmic inflation, the epoch in the universe's first trillionth of a trillionth of a trillionth of a second that set the initial conditions for everything that followed. The seeds of structure in the universe were planted in inflation. If the seeds that produced the TON 618 system were larger than standard inflation predicts, then our model of inflation was either wrong or incomplete. The reclassification pulls on a thread. The thread is connected to something much deeper than a single object. Pull hard enough, and the foundations move. Part 7. The visual horror. What you would see this is the part where we step away from the equations for a moment and try to see this. Not because the visual helps the physics. It does not. The physics is what it is, regardless of whether a human brain can form an intuitive image of it. But there is something important about attempting the visualization and encountering where it fails. Because where the imagination fails is precisely where the reality is most different from anything we have encountered before. Imagine you are somewhere above the TON 618 system. Not close, close would kill you, and we will get to the specifics of that shortly. Above it, looking down at the scale of the system the way you might look down at a city from a great altitude. The primary black hole is below you, and even at this distance, it is not visible as a shape. What you see is the accretion disk, the blazing, superheated disk of infalling matter that extends for light days in every direction from the event horizon. From above, the disk appears as a brilliant, flattened ring of light, intensely bright at its inner edge, where temperatures reach millions of degrees and where the gas moves at a significant fraction of the speed of light, fading to deep orange and then dim red at its outer edges, where the material is cooler and moving more slowly. The disk is not perfectly flat. The inner regions are turbulent. Magnetic fields thread through it in complex patterns. Jets of material, accelerated to near-light speed by those fields, shoot outward perpendicular to the disk plane. Pillars of hot plasma extending for hundreds of thousands of light-years in both directions, carrying energy away from the system, punching holes in the surrounding gas, heating the intergalactic medium. Now, offset from that, separated by what would appear from your vantage point as a significant angular distance, though in absolute terms the separation is tiny compared to the distances involved, is the second source. Less brilliant, partially obscured. A dimmer accretion disk, the telltale infrared glow of a galaxy host, and at its center the same basic structure, an event horizon, a feeding black hole, an energy budget that would make our own Milky Way's central black hole look like a flashlight held next to a star. The two of them are orbiting each other. The period of that orbit, for two objects at the mass and separation implied by the data, would be millions of years. Millions of years for one complete circuit. From your vantage point above the system, you would not be able to perceive the orbital motion at all. The system would appear static. Only time-lapse over millions of years would reveal the slow spiral. But it is spiraling. Both objects are radiating gravitational energy. Both are losing orbital momentum. Both are falling infinitesimally slowly on any human timescale toward the moment of merger. The merger itself, The moment when the two event horizons make contact, when the inspiral accelerates past any possibility of reversal, when the two black holes become one in a collision that releases more energy than any other event in the post-Big Bang universe, would be the most violent thing you can imagine, and also the most invisible. Gravitational waves are invisible. They do not carry photons. They pass through matter without interaction. The merger would release its energy into the fabric of space-time, not into the electromagnetic spectrum. From your vantage point above the system, if you could somehow be there at the moment of merger, you would see the two accretion disks suddenly distorted as the gravitational geometry of the region changed catastrophically. You would see the jets disrupted. You would see a surge of electromagnetic radiation as the disrupted accretion material was suddenly exposed to an event horizon whose size had doubled. And then, in what would feel like a geological instant by cosmic standards, the new combined system would settle into its post-merger configuration. One event horizon, one accretion disk, one black hole with the combined mass of both predecessors, sitting at the center of a combined galaxy, burning through whatever accretion material the merger had kicked into chaotic new orbits, blazing more luminously than before. The gravitational waves from all of this would have already left, propagating in all directions at the speed of light, carrying the news of what happened to anyone with instruments sensitive enough to receive it, including, potentially, us. If the merger happened 8 billion years ago, 4 billion years after TON 618's light left its source, those gravitational waves would arrive here in approximately 2 more billion years, long after the Sun has left the main sequence, long after Earth, in any recognizable form, is gone. If the merger happened more recently, say, in the universe's current epoch, the waves are approaching right now, and they will arrive in approximately 10 billion years, at the universe's age of 24 billion years, assuming a technological civilization still exists somewhere to detect them. If the merger has not happened yet, if the inspiral is still ongoing in the current universe, then future observers with future instruments will one day see the signal arrive, and know that the most extreme merger in the observable universe has just completed. We cannot know which of these is true. The wall of light travel time between us and TON 618's current state is absolute. It is not a solvable problem. It is a fundamental limit on what knowledge is possible from our location in the universe. The wall is real. We stand on this side of it. Part 8. The dark matter architecture underneath everything. To understand why the binary interpretation of the TON 16 system is not merely an extreme curiosity but a structural problem for cosmology, we need to spend time with the invisible scaffolding that organizes everything visible in the universe. We need to talk about dark matter. Dark matter is not a placeholder for ignorance. It is a specific observational fact dressed in an explanatory gap. The observation is this: galaxies rotate at speeds inconsistent with the gravity of their visible mass alone. Galaxy clusters bend light at angles inconsistent with the gravity of their visible mass alone. The large-scale structure of the universe, the cosmic web of filaments, sheets, walls, and voids that organizes matter on scales of hundreds of millions of light-years, matches precisely the structure you would predict if approximately 5 times as much dark matter as visible matter was present, distributed in specific ways, governing the gravitational landscape in which ordinary matter moves. The cosmic microwave background, the echo of the Big Bang, the oldest light in the universe, carries imprinted in its temperature fluctuations the exact pattern of density variations in the early universe, and that pattern matches a universe dominated by cold dark matter with the kind of precision that makes cosmologists unusually confident. Dark matter is real. We do not know what it is made of. We know where it is. We know how much there is. We know how it behaves gravitationally. We know it does not emit or absorb light. Beyond those facts, it is a box labeled unknown contents that nonetheless correctly predicts the structure of the universe at every scale we have been able to test. The dark matter halo is the container in which every galaxy and every galaxy group exists. Before there were stars, before there were atoms assembled into molecular clouds or dust or planets, the dark matter had already organized it itself into halos of various masses, distributed according to the statistics of quantum fluctuations in the inflationary epoch. The baryonic matter, ordinary matter, the kind you are made of, fell into those dark matter halos under gravity, cooled, condensed, and eventually formed stars and galaxies. The dark matter halo came first. The galaxy came second, built inside the halo the way a pearl builds around a grain of sand. For the lambda CDM model, this sequence is well defined. The distribution of dark matter halo masses at any given cosmic epoch follows a specific function, the halo mass function, that has been computed and tested against observations extensively. At any redshift, the model predicts how many halos of what mass should exist. At the redshift of TON 16, the model makes specific predictions about how massive a dark matter halo can be. The revised TON 618 system, the host galaxy at its revised mass, the proposed binary central black hole, the overdense surrounding structure, implies a dark matter halo more massive than the lambda CDM halo mass function predicts at that redshift. Not slightly more massive, not within the scatter of the distribution. More massive in a way that places the TON 618 system at or beyond the exponential tail of the predicted distribution, where exponential tail means there should be vanishingly few such halos in the observable universe. But here is the key word, should. The model says should be vanishingly few. The observation suggests there is one, and the emerging population of early massive galaxies and early massive black holes across the Webb deep fields suggests there are more, not vanishingly few, a statistically meaningful population. A population whose number exceeds the model's predictions in the same direction, at the same redshifts, at multiple mass scales. The exponential tail of a distribution is where the model is most sensitive. Small changes in the initial conditions, in the amplitude and shape of the primordial power spectrum, in the parameters governing dark matter's behavior on small scales, in the efficiency of converting dark matter halo mass into baryonic structure, produce large changes in the tail. If the observations are consistently showing more halos at the massive end than the model predicts, the most natural interpretation is that the primordial power spectrum had slightly more power at specific scales than the standard model assumes. Not wildly different, not enough to disrupt the model's success in explaining the CMB or the overall large-scale structure, just slightly more power, at specific scales, enough to shift the tail of the halo mass distribution by a meaningful amount. The specific scales in question correspond to the masses of objects like the TON 618 system's proposed dark matter halo. The implied modification to the primordial power spectrum, if the binary interpretation is correct and the host galaxy mass revision is accurate, points toward a slightly non-standard inflationary history, or a slightly non-standard dark matter model, operating at the scale of massive galaxy formation. This is not a crisis, it is a signal embedded in the most extreme object in the observable universe, amplified by the reclassification, pointing at the piece of our cosmological model that needs adjustment. Finding that piece is work that will take a generation, but the direction is becoming clearer with every new instrument and every new data release. TON 618 is not just a curiosity, it is a cosmological instrument, pointed backward in time, measuring something fundamental about the conditions at the universe's beginning. Part 9. The feedback loop and why both problems feed each other. The growth of a black hole and the growth of the galaxy that contains it are not independent processes. They are coupled by what astrophysicists call feedback, the mechanism by which the energy output of the growing black hole regulates the conditions in the surrounding galaxy, which in turn regulates how much matter is available to feed the black hole, which in turn regulates how much energy it outputs. It is a loop, and like most loops in nature, it has stable states and unstable states, runaway modes and self-limiting modes, and the difference between them determines whether a galaxy and its central black hole grow slowly and modestly, or grow rapidly and to extreme sizes. Here is how it works in the ordinary case. Gas falls into a galaxy's dark matter halo from the surrounding intergalactic medium. It cools and condenses, forming molecular clouds. Molecular clouds collapse under gravity to form stars. Stars form at a rate set by the balance between the gravity pulling the gas together and the pressure from stellar radiation and supernova explosions pushing it apart. The most massive stars live brief, violent lives and explode as supernovae, heating the surrounding gas and temporarily halting star formation in their vicinity. The overall star formation rate is regulated by this balance. Meanwhile, some fraction of the gas that falls into the galaxy does not form stars. It falls deeper, into the central gravitational potential of the dark matter halo, where it encounters the central black hole. It forms an accretion disk. The accretion disk feeds the black hole and in doing so releases energy, as radiation, as jets, as winds, that heats the surrounding gas. That heating reduces the cooling rate of the gas, reducing the rate at which gas can condense into the accretion disk, reducing the feeding rate of the black hole, reducing the energy output. A self-limiting cycle. At the scale of the Milky Way's central black hole, Sagittarius A, 4 million solar masses, this feedback is relatively mild. The black hole is large enough to influence the gas dynamics in the innermost kiloparsec of the galaxy, but the galaxy as a whole barely notices. The black hole's energy output is orders of magnitude less than the star formation luminosity of the surrounding disk. At the scale of TON 618 and now potentially the combined scale of a TON 6T binary system, the feedback is not mild, it is catastrophic. The energy output of a quasar at this luminosity is not negligible compared to the galaxy's energy budget, is comparable to it, or exceeds it. The jets from an active quasar of this power do not heat the innermost kiloparsec. They punch through the galaxy's gas reservoir entirely, and heat the surrounding intergalactic medium across hundreds of thousands of light years. The radiation pressure from the accretion disk accelerates large-scale winds that sweep gas out of the galaxy's potential well, terminating star formation not in one region but across the entire galaxy on a timescale of tens to hundreds of millions of years. This is called quasar mode feedback. It is the mechanism by which the most massive black holes in the universe are thought to have shaped the galaxies around them, shutting off star formation when the black hole grew large enough, producing the old, red, quiescent elliptical galaxies we observe at the centers of galaxy clusters today. Now apply this to the TON 618 system. If the system is indeed a binary, two quasars active simultaneously in the same host galaxy, then the feedback energy input to the surrounding galaxy is doubled or more. Two jets, two accretion disk winds, two radiation fields heating the gas. The combined feedback power from a binary ultramassive quasar system in a galaxy of the revised host mass would be capable of sweeping the gas reservoir of not just the host galaxy but the surrounding group environment, potentially terminating work across the entire overdensity that the system sits within. One binary quasar powerful enough to shut down star formation across an entire galaxy group. And here is the further implication. If the TON 618 system is representative of a class, if there are other binary ultramassive systems in the early universe producing the gravitational wave background amplitude that NANOGrav detected, then the integrated feedback energy from that population into the intergalactic medium of the early universe was larger than current models account for. The thermal state of the intergalactic medium, the rate of star formation in early massive galaxies, the speed at which those galaxies transitioned from active star formation to quiescence, all of those depend in part on the energy input from quasar feedback. If the feedback was larger and more extreme than the single quasar models assumed, then the early universe's thermal history was different. Different in ways that would show up in the properties of early galaxies, in the specific pattern of when massive galaxies stop forming stars, in the temperature of the intergalactic medium at specific redshifts, in the absorption patterns of quasar light passing through intervening gas, the Lyman alpha forest, the spectral fingerprint of gas along cosmic sightlines. All of those observations exist. They are in the archives. The teams working on the TON 618 reclassification are now looking at whether the binary interpretation, combined with a revised feedback model, can explain any of the residuals, the places where the standard single quasar feedback model slightly misfits the data. If it can, that would be additional evidence for the binary interpretation and for the broader class of ultramassive binary systems in the early universe. If it cannot, if the feedback signatures are inconsistent with what a binary system would produce, that would be evidence against the binary interpretation and a reason to look for other explanations for the second source. Either way, the question is now being asked with specific predictions attached. That is what reclassification does at its best. It does not just change a label, it generates new tests. Part 10. The post-merger universe and what comes after it is worth spending time now with what happens after the in-spiral ends, after the two event horizons touch, after the most energetic non-Big Bang event in the universe's history has occurred, and the gravitational wave burst has propagated outward, and the combined black hole has settled into its new configuration. What does the universe look like at that location in the aftermath? The first thing to understand is the time scale of the merger itself. The final plunge, the phase where the orbital separation shrinks from a few gravitational radii to merger in the formal sense, occurs on a timescale comparable to the orbital period at that separation. For two objects of this mass, the orbital period at a separation of a few gravitational radii is measured in days to weeks. The merger, in the cosmic sense, is instantaneous. A universe that had spent hundreds of millions of years slowly spiraling two ultramassive black holes toward each other watches the finale in days. The gravitational wave burst is over. The combined black hole, the new single entity whose mass is the sum of the two progenitors, minus the energy radiated away in gravitational waves, which amounts to a few % of the total mass, is now a single larger, quieter thing. Its event horizon encompasses a sphere with a radius corresponding to the combined mass. It is in a state of extreme perturbed ringdown. The formal technical term is ringdown, and it refers to the oscillations of the newly formed black hole's event horizon as it settles from the distorted asymmetric shape produced by the merger into the smooth, steady Kerr geometry of a spinning black hole in equilibrium. The ringdown produces a characteristic gravitational wave signal, a rapid exponential damping of oscillations at specific frequencies set by the mass and spin of the final black hole. The ringdown signal is brief. For a black hole of this combined mass, it lasts on the order of seconds to minutes in its own frame. The signal propagates outward with the rest of the gravitational wave burst. Then there is the electromagnetic counterpart. The merger disrupts the accretion geometry of both progenitor black holes. The two accretion disks, which have been organized around their respective centers of mass, are suddenly exposed to the gravitational field of a new combined asymmetric object that is briefly oscillating and radiating gravitational waves and delivering gravitational recall kicks to the surrounding material. The accretion material is violently disrupted. Some of it is flung outward into the surrounding galaxy. Some of it falls inward toward the new combined event horizon on chaotic, non-circular orbits. Some of it collides with itself, shocks, heats to extreme temperatures, and produces a burst of electromagnetic radiation that briefly makes the merged system even more luminous than the sum of the two progenitors was before. This electromagnetic flare, the quasar equivalent of a bell ringing when you strike it, lasts for months to years before the new accretion geometry settles into a calmer configuration. During the flare, the system is brighter, more variable, and spectrally different from either progenitor alone. If we were observing the TON 618 system at the moment of its merger, which we are not because we are looking at 10 billion-year-old light, but hypothetically, we would see it brighten, become more variable on short timescales, show spectral features consistent with the disrupted accretion geometry, and then gradually settle back to a new steady state. That new steady state is a single ultramassive quasar, larger than either progenitor, continuing to feed from whatever gas reservoir the merger left undisrupted. The merged system is, in a sense, not the end of the story. It is a new beginning for an even more extreme single object. The merged black hole, feeding from the combined host galaxy's gas reservoir, will continue to grow, it will continue to emit, it will continue to send light and gravitational waves outward in every direction, contributing to the gravitational wave background, shining in any instruments pointed at its location, sending its story across the expanding universe in photons and space-time ripples for as long as it has matter to feed on. The largest known black hole in the universe, if the binary interpretation is correct, is not yet fully assembled. The largest known black hole in the observable universe is still in the process of becoming what it will eventually be. We have caught it in the act. Part 11. The human dimension of the incomprehensible. There is a peculiar cognitive difficulty that arises whenever someone tries to genuinely comprehend an object of TON N618 scale, and it is worth naming because it is not a failure of intelligence. It is a feature of how human cognition works, and the failure to name it produces a kind of false familiarity, the sense that you understand something because you have learned the numbers, when in fact the numbers have been processed by the same brain regions that handle the prices of groceries and the distances to the next town, and those brain regions were not designed for the task. The number 66 billion solar masses does not produce, in the mind that encounters it, any response proportional to 66 billion solar masses. It produces a response proportional to the number 66 billion, which is a large number in the context of household finances, but is an abstract symbol when applied to the mass of gravitational objects at cosmological distances. The brain registers very large and moves on. The very large registered for 66 billion solar masses is not qualitatively different from the very large registered for 1 billion solar masses, or 10 trillion solar masses. The numbers are too far outside the range of direct experience to produce calibrated emotional responses. This is not a bug in human cognition. It is the expected behavior of a sensory system designed for the environments that our ancestors survived in, which did not include environments where distinguishing between 1 billion and 1 trillion had survival value. The cognitive shortcut, treating all very large numbers as very large without tracking their relative magnitudes, was not costly in those environments. It is costly now, when understanding the universe requires holding magnitudes apart that differ by factors of millions. The only solution is deliberate translation, and the translations have to be physical, anchored in experience, using objects that the imagination can actually hold. So try this. You are standing in a field on a clear night, far from any city. The Milky Way is visible overhead, its dusty arms stretched across the sky from horizon to horizon. Every point of light you can see is a star. Some of them are as small as our sun. Some are dramatically larger. Some are hundreds of times brighter. Every one of them is at least several light years away. The farthest individual star visible to your naked eye under perfect conditions is perhaps a few thousand light years away. Beyond that, individual stars blur into the general glow of the galaxy. There are roughly 400 billion stars in the Milky Way. Most of them are invisible to you because they are too far away, because intervening dust blocks their light, because the sky is not dark enough anywhere on Earth to show you the faintest ones. What you can see is a tiny fraction of a tiny fraction, a few thousand points of light in a galaxy of 400 billion suns. Now consider that the mass of the proposed TON 618 binary system, the combined mass of the primary at 66 billion solar masses and the secondary at approximately 30 billion, exceeds the total stellar mass of the Milky Way by a factor of more than 200. You would need to combine more than 200 Milky Ways. Every star in every one of them, every brown dwarf, every neutron star, every white dwarf, every object down to the smallest stellar remnant, and pour all of that mass into 2 points to create something comparable to what we think we are looking at in the TON 618 system. 200 Milky Ways. The field you are standing in, under all those stars you can see, is inside one Milky Way. Everything you have ever known as a reference for the scale of the universe, the stars, the constellations, the galaxy's arm above you, the entire collection of 400 billion suns, is less than half of 1% of the mass in that distant system. The stars above you are not even a rounding error. This is not meant to diminish the night sky. The night sky remains one of the most profound experiences available to any organism with the nervous system to appreciate it. But the honest response to TON 618, the emotionally accurate response, if you could build an emotional system calibrated to the actual magnitudes, would not be awe. AOE is too small. There is not a word in any human language for what the correct emotional response to 66 billion solar masses actually is, because no human has ever needed to develop one, because nothing in any human environment has ever required a calibrated emotional response to scales of that magnitude. The languages we have were built for human-scale experiences. The universe is not a human-scale experience, and the gap between the two is not closing as our instruments improve. It is, if anything, widening. The better we look, the more extreme the extremes turn out to be. The deeper the universe goes, the more clearly it shows that the vocabulary we have for describing it was built for a much smaller room. We are using words for something that requires different words. We are using concepts built for survival on a rocky planet to describe gravitational objects 100 billion times more massive than the star our planet orbits. And yet, and this is worth holding at the same time, we are doing it. We built the instruments. We sent one into orbit at the L2 point 1.5 million kilometers from Earth. We trained the detectors, designed the filters, wrote the spectral analysis pipelines, developed the dynamical models, and extracted from the faint infrared glow arriving from 10 billion light-years away the specific fact that there appears to be a second source at the same redshift as the most massive object we have ever found. A civilization of organisms whose brains evolved to track predators and remember where the food was in a landscape of roughly 50 kilometers across. A civilization of organisms who have been doing organized astronomy for less than 300 years, detected a binary companion to a black hole 10 billion light-years away. That deserves to sit alongside the incomprehensibility of the scale it revealed. The smallness that discovered the enormousness is, in its own way, as hard to process as the enormousness itself. Part 12. What the reclassification means for future search is the immediate scientific consequence of the TON 618 reclassification. Beyond what it tells us about this specific system, is what implies for how we search for other extreme objects. Reclassification changes the search strategy. Before the reclassification, the approach to identifying the universe's most massive black holes was relatively straightforward. Find the brightest quasars at the highest redshifts, measure their redshifts, infer their luminosities, estimate their masses from the luminosity using established correlations, and catalogue them. That approach found TON 618 as a single, solitary source, the most extreme point in the catalogue, separated from everything else by a significant margin. After the reclassification, after the discovery that a second source was hiding in the infrared data all along, the approach has to change. Every single entry in the catalogue of extreme high redshift quasars becomes a candidate for a binary companion. Every one of them was characterized using optical instruments that could not resolve structure at the scales where a binary companion might sit. Every one of them was measured in wavelength ranges where a dust-obscured companion might be invisible. Every one of them might have a second source hiding in the wings of its point spread function. This is not a small concern. There are thousands of quasars in the current catalogues at redshifts above 1. There are hundreds at redshifts above 2. There are dozens at redshifts above 3, where the masses are most extreme and the formation paradox is most acute. Every one of them needs to be re-examined with the depth and sensitivity and infrared capability that revealed the second source at 618. Webb cannot observe all of them in the time available to a single space telescope, but it can observe the most extreme ones, the ones at the highest redshifts and largest estimated masses, the ones that are, like TON 618, already impossible by the standard growth models, and therefore most likely to be hiding additional complexity. The teams working on the TON 618 second source are already planning a systematic survey. not just of TON 618's neighbours in the catalogue, but of the entire population of ultramassive high redshift quasars that Webb has access to. The goal is to determine the binary fraction, the fraction of ultramassive quasars that, when examined with sufficient sensitivity in the infrared, turn out to have binary companions. If the binary fraction is low, if TON 618 is one of a handful of unusual binary systems in the high redshift quasar catalogue, the reclassification is a significant finding about one object, but does not fundamentally alter the population-level picture. If the binary fraction is high, if a substantial fraction of ultramassive high redshift quasars turn out to have hidden infrared companions when examined with Webb's sensitivity, then the catalogue of extreme early black holes needs to be systematically revised. The mass estimates, based on the assumption of single sources, may be underestimates for a large fraction of the population. The formation paradox, already acute, becomes more acute across the entire high-mass end of the quasar distribution. The contribution to the gravitational wave background from this population increases substantially. The answer to that question will come from observation programs currently being planned and executed. The data will be in the archives within the next few years. The analysis will follow. The conclusions will arrive, peer-reviewed and debated and refined, in the scientific literature. And then there will be another reclassification, or several, or many, and the picture will change again. The picture always changes. That is not a weakness of science. That is science functioning as designed. Part 13. The silence between the messages here is something that does not usually get mentioned in the popular account of astronomical discovery, and that is worth mentioning now, because it changes the emotional register of the whole story. For most of the 10 billion years that TON 618's light has been travelling toward us, there was no one here to receive it. Not for the first 3 billion years of that journey, while the solar system was forming, and the Earth was a molten ball bombarded by debris. Not for the following 3 billion years, while the first life on Earth was single-celled, and then multicellular, and then beginning the long, slow process of evolving complexity without anything resembling a nervous system capable of abstract thought. Not for the billion years after that, as the first animals and then the first vertebrates appeared, still nowhere near the cognitive threshold required to understand the concept of light from a distant galaxy. For roughly 9.5 billion of the 10.5 billion years of the photon's journey, there was nothing on the receiving end capable of making sense of them. They arrived at a planet that did not exist, or that existed but hosted only organisms that could not conceive of what a photon was or where it had come from. The first human who might have glanced in the direction of TON 618's coordinates and recognized them as carrying information about something distant was, perhaps, an ancient astronomer who saw a faint star-like point in the sky and wrote it down in a list. That person knew nothing of what they were looking at. The photons arrived. They landed in human retinas or bronze or clay tablets, and left no trace of their 10 billion year journey because the receiving apparatus had no way to decode the message. For most of the journey, the message was not received in any meaningful sense, not by any mind capable of understanding it. The photons did not mind. Photons do not mind. But there is something in that history worth holding. The vast, silent majority of the journey, the billions of years of travel toward a planet that was not ready to understand what was being sent, that adds a dimension to the photons that arrived tonight. The photons arriving tonight at Webb's detectors are the first photons from 618 to be received by minds capable of extracting from them the information they carry. The mass of the source, its redshift, its host galaxy, and now the possible existence of a companion. Every photon that arrived before the last 100 years of astronomical instrumentation landed without being fully decoded. The full message, the 70-year accumulation of observations, the Webb reclassification, the binary hypothesis, all of it, is accessible only to the last few generations of observers, the last fraction of the journey's duration. We are, in cosmological terms, the first minds positioned to hear this. The message has been travelling for 10 billion years, and the receivers capable of decoding it have been here for roughly a century. That is humbling in a way that the scale numbers alone do not fully capture, not just the scale of the object. The scale of the gap between when the message was sent and when it could first be meaningfully received. 10 billion years of travel to reach a civilization that has been capable of decoding the signal for 100 years. 100 years, out of 10 billion. The photons barely made it in time. Part 14, what comes next, and what it will show. Let us widen the frame. Not just TON 618, the full picture of what the recent data is showing across the early universe. Because the TON 618 reclassification does not exist in isolation. It exists in a context that has been building for 3 years, and the context is what makes this a different kind of problem from one anomalous object. The host galaxy of TON 618 in the previous model was assumed to be a large but not extraordinary galaxy of the type you would expect to find hosting a quasar of this luminosity at this redshift. In the revised analysis using the Webb infrared data, the stellar mass profile of the host, the total mass of stars in the galaxy, the dark matter halo that contains it, the gas reservoir available for star formation and black hole feeding, came back approximately 70 to 80% larger than the older models assumed. 70 to 80%. This is not a calibration tweak. This is not an instrumental correction. If you have a model that predicts the mass of a galaxy, and your observation comes back 70 to 80% higher, the model did not have a small error. The model was missing something. Either the galaxy formation process in this overdense region of the early universe was operating in a mode the model does not include, or the dark matter halo that hosted this system was more massive than the model's initial conditions produced, or the efficiency of converting gas into stars and feeding into the central black hole was higher than the model's feedback prescriptions allow. Any of those explanations requires adding new physics to the model or revising the parameters that govern the existing physics in ways that ripple through the model's predictions for everything else. A galaxy that massive, assembled that early, at a cosmic age of 3.5 billion years, is not a normal early galaxy. It belongs in a specific growing catalogue of objects that are collectively called early massive galaxies, and they have been a problem for cosmologists since the first generation of deep field data started coming in from Webb's infrared detectors. Here is the scope of that problem. In the standard lambda CDM cosmological model, the cold dark matter model that has been the foundation of cosmology for 30 years, galaxy growth is hierarchical. Small structures form first, driven by the gravitational collapse of small dark matter halos. Those small halos merge into larger halos. The baryonic matter, the gas, the atoms, the stuff that stars are made of, follows the dark matter, cooling and condensing in the halos' gravitational wells, forming stars, forming the first small protogalaxies. Those protogalaxies merge into larger galaxies. Those larger galaxies merge into the massive ellipticals at the centers of galaxy clusters. The process is gradual, hierarchical, bottom-up, spanning billions of years. The most massive galaxies in the present-day universe, the giant ellipticals sitting at the centers of rich galaxy clusters, assembled their final masses over many billions of years, through many merger events, accumulating their stellar populations slowly. But Webb is finding galaxies that are already massive at redshifts of 10, 11, 12, at cosmic ages of only a few 100 million years, before the hierarchical assembly process could possibly have had time to build them. Not marginally more massive than expected, several times more massive in some cases. Fully assembled stellar populations, already burning through their gas, already old, in a universe that by the model's timeline should be populating only the first tiny protogalaxies. The discrepancy is not a few exceptional objects, it is a statistical population. It is a systematic excess of massive early galaxies that grows as the data gets better. Every deep field image Webb returns contains more of them than the models predict. This is the galaxy version of the black hole formation problem. And the two problems are connected, because the black holes and the galaxies they live in grow together. The feedback between a growing central black hole and its host galaxy, the heating of surrounding gas by quasar radiation, the sweeping of gas by jets, the regulation of star formation by the energy budget of the active nucleus, means that the growth histories of the black hole and the galaxy are coupled. If the galaxy assembled too fast, the black hole probably grew too fast. If the black hole grew too fast, it was probably fed by a galaxy that assembled its gas reservoir too quickly. The two anomalies are aspects of the same underlying process. And that underlying process, whatever it is apparently operating everywhere in the early universe that Webb is looking, not just in the specific location that produced TON 6 and 18. Part 9. The little red dots and what they are telling us. Since Webb began returning deep field data, astronomers have been encountering objects that are informally called little red dots. That name is a placeholder for something that is not friendly and has no better name yet. The little red dots are compact, reddish sources found at redshifts corresponding to the very early universe, some of them at cosmic ages of only a few 100 million years. They are small in angular extent even for Webb's capabilities. They are red because the high-energy emission from their central sources has been absorbed by dust, and what reaches us through the dust is the longer wavelength reddened glow. And they are, by spectroscopic analysis, active. They emit the broad emission lines that are the diagnostic signature of an active galactic nucleus, a central black hole that is currently feeding. The spectral lines are broad because the gas near the black hole is moving at thousands of kilometers per second under the black hole's gravity, and that velocity spreads the emission across a range of wavelengths. The mass estimates for the black holes powering the little red dots span a range. But the objects that have drawn the most attention are those with masses in the hundreds of millions to several billion solar masses. Black holes of several billion solar masses existing in the universe at ages of only a few 100 million years. Several 100 million years after the Big Bang, in a universe that was still in the first few percent of its current age, something was already powering active galactic nuclei at black hole masses our models do not produce until much later. Webb finds these objects with uncomfortable regularity. Every new deep field survey turns up more of them. The number has grown from a handful of interesting anomalies to a statistical population that represents a systematic excess over model predictions. In some mass ranges and some redshift bins, the observed number of active massive black holes exceeds the predicted number by factors of 10 to 100. Now add the TON 618 reclassification to this picture. The little red dots represent one extreme of the problem. Black holes of billions of solar masses, too early. TON 618 represents the other extreme. A possible binary system of combined mass approaching or exceeding 100 billion solar masses in a host galaxy more massive than models allow, at the center of a cosmic overdensity larger than predicted. Between those two extremes sits a continuous distribution of anomalously massive early black holes found throughout the observable early universe in every direction Webb has pointed. The early universe was not the gentle, slowly assembling nursery our models described. It was violent, it was fast. It was productive of enormous structures at a rate and scale that our best physics cannot justify. And it was doing this not in isolated, special locations, it was doing it everywhere. The pattern is the problem, not the individual data points. When one object exceeds model predictions, it is an outlier. When a statistically significant population of objects across the entire sky, in every deep field survey, systematically exceeds model predictions at multiple cosmic epochs and multiple mass scales, you are not looking at outliers. You are looking at evidence that the model is missing a term, a physical process, a mode of growth or formation or structural assembly that was operating in the early universe at scale, unaccounted for in the equations we currently use. TON 618 is not the anomaly. TON 618 is the most visible example of a pattern that runs through the entire early universe. Its reclassification from single impossibly massive object to possible binary impossibly massive system in an impossibly massive host galaxy in an impossibly large cosmic web node is not a story about one strange object. It is a story about the discovery that the strangeness is everywhere. Part 10. The gravitational wave background and its implications. In 2023, several independent pulsar timing array collaborations made an announcement that received less public attention than it deserved. The NANOGrav collaboration, along with European, Indian, Chinese, and Australian counterparts working with their respective arrays of millisecond pulsars, presented data showing something that cosmologists had been searching for and expecting, but that, when it actually arrived, was still somehow surprising. The universe has a gravitational wave background, not a single event, not a handful of detections. A persistent, omnipresent, isotropic signal pervading all of space-time, detectable by measuring the correlated timing deviations of millisecond pulsars across the Milky Way. Millisecond pulsars are neutron stars spinning hundreds of times per second, stable enough to function as cosmic atomic clocks. When a gravitational wave passes through the Milky Way, it stretches and compresses space-time, and that compression shifts the arrival times of pulsar signals by tiny amounts. By measuring those shifts across an array of pulsars in different directions, you can detect the wave even when its individual effect on any one pulsar is too small to identify independently. The background signal was detected. The statistical confidence is overwhelming. The universe is humming with gravitational waves at frequencies too low for LIGO to detect, nanohertz frequencies, billionths of a cycle per second, that pervade the cosmos continuously. The most natural and theoretically compelling explanation for the gravitational wave background is a cosmic population of supermassive binary black holes. Billions of pairs of supermassive black holes in billions of galaxies throughout the universe, all slowly spiraling toward merger, all radiating gravitational energy at low frequencies, all contributing to a combined background that adds up to the signal the pulsar timing arrays have detected. The universe's most massive objects, falling toward each other everywhere all at once, have filled space itself with a low hum of gravitational radiation, the sound of black holes falling. Now add the proposed TON 618 binary to this picture. A system of combined mass approaching or exceeding 90 billion solar masses would not contribute to the gravitational wave background in proportion to its mass. The gravitational wave luminosity scales with the square of the masses and the inverse of the orbital separation. At the extreme mass end of the binary black hole population, individual systems contribute disproportionately to the background signal. A system like the proposed TON 618 binary would be among the loudest individual contributors in the entire observable universe. Its signal, while not individually separable from the background with current pulsar timing array sensitivity, would account for a detectable fraction of the total background amplitude. The current models of the gravitational wave background, the models that take the known distribution of supermassive black hole masses in galaxies, the known merger rates, and the known orbital dynamics, and predict what the background spectrum should look like, are tested by the NANOGrav data, and they mostly fit. But there is tension. The amplitude of the observed background is on the higher end of what the models predict. The spectrum has features that are not fully accounted for by the standard population models. If there is a population of ultramassive binaries, objects in the mass range of the proposed TON 618 system existing in the early universe, contributing their outsized gravitational wave luminosity to the background, then those objects would push the predicted background amplitude upward in the direction of the observed tension. The TON 618 reclassification, the NANOGrav background signal, the Webb-discovered population of early massive black holes, these are not three separate puzzles. They are three views of the same puzzle. A puzzle that involves the early universe producing massive black holes and massive binary systems at a rate and scale that our standard model underestimates, creating a gravitational wave background that is slightly louder than simple models predict, leaving behind a population of anomalously massive early galaxies, and producing at least one system, and possibly many, at the extreme high end of what physics allows. The puzzle has edges now. We are beginning to see its shape. We do not yet know what picture it contains. Part 11. The physics that might fix this three categories of explanation are being seriously explored by researchers working on the formation paradox, the early galaxy mass excess, and the gravitational wave background tension simultaneously, because those problems appear to share a common root. The first category proposes that standard physics can account for the observations if certain parameters are pushed to their extreme schemes. The relevant extreme in this case is accretion physics. The Eddington limit, the maximum accretion rate, the rate at which radiation pressure halts further infall, is not a hard physical law. It is a condition derived from assuming spherically symmetric accretion with a standard radiation field. When the geometry deviates from that assumption, when matter falls in through a narrow channel while radiation escapes through the polar directions, when magnetic fields modify the radiation transfer, when the accretion disk becomes geometrically thick rather than thin, the effective accretion rate can exceed the Eddington limit by factors of a few to several hundred. Super Eddington accretion is real. It has been observed in specific types of systems. The question is whether it was widespread enough in the early universe to account for the population-level excess of massive black holes. The answer, based on the observational evidence, is probably not by itself. Some early black holes show signs of super Eddington accretion. The population-level statistics do not cleanly match a universe where it was the dominant growth mechanism for all of them. The second category modifies the initial conditions. Larger seeds, direct collapse black holes of 100,000 solar masses or more, or primordial black holes formed in the earliest moments of the universe, remove the most extreme version of the growth rate problem. With a larger starting mass, reaching tens of billions of solar masses in 3.5 billion years, requires a challenging but not mathematically impossible sustained growth rate. The difficulty is explaining how enough large seeds formed in the early universe to account for the full population of anomalously massive black holes that Webb is finding. The number required is large. The mechanism for producing that many large seeds is not well established. The third category, and the most structurally significant, proposes that the cosmological background itself, the large-scale dynamics of dark matter, dark energy, and the primordial density field, behave differently in the early universe than lambda CDM predicts. Specifically, that structure formation was faster and more efficient in the early universe than the standard model allows. Dark matter halos collapsed earlier. Gas cooled more efficiently. The density fluctuations that seeded all structure were larger in amplitude at certain scales. Some or all of these modifications, if operating in the early universe, would produce faster galaxy assembly, faster black hole growth, more massive structures at earlier epochs, and a larger population of ultramassive binaries, with all the downstream consequences for the gravitational wave background, the little red dots, and the TON 618 system. The modifications required are not wild departures from lambda CDM. They are adjustments, changes to the initial amplitude or shape of the primordial power spectrum, alternative dark matter models that cluster differently on small scales, warm dark matter, fuzzy dark matter, self-interacting dark matter, modifications to the reionization history, small changes to the coupling between dark energy and dark matter that were more significant in the early universe than today. Any of these modifications would propagate through the entire cosmological model and make specific predictions elsewhere, predictions that can be tested against CMB data, large-scale structure surveys, and the precise spectrum of the gravitational wave background. Finding a modification that simultaneously explains the early universe mass excess, the gravitational wave background amplitude, and the TON 618 system properties, without violating any of the constraints from later epoch observations, is a constrained optimization problem of considerable difficulty. But it is the kind of problem that gets solved, slowly, with data, with a generation of researchers who decide that inconsistencies is real and important and worth pursuing rather than footnoting. The reclassification of TON 8 adds urgency to that pursuit. It adds data, it adds constraints. It narrows the range of possible solutions by adding another requirement that any successful theory must meet. There is a new flaw on how extreme the early universe was, and the flaw just moved down. Part 12. What you would not survive. We have been careful to establish that none of this is a direct threat to Earth, or to any organism on it or near it. The distances are too large. The physics of the interaction over those distances is benign. We establish that. We mean it. But there is a question that follows from the scale descriptions, the binary hypothesis, the merger energetics, that keeps surfacing and deserves a direct answer. What would happen if you were near this system? Not on Earth, near it. In the vicinity of an active merger of two ultramassive black holes. The answer is not something your imagination will produce without assistance. Start with the accretion disk of the primary. The radiation environment around an active quasar of TON 618's luminosity at distances within a few hundred light-years would be lethal to any biological organism by virtually any definition of that word. The X-ray and ultraviolet radiation flux from the accretion disk at close range exceeds the threshold for ionizing damage to molecular structures, DNA, proteins, lipids, all of the chemical architecture of life, by many orders of magnitude. The secondary radiation from interactions between the hard X-rays and surrounding gas would add gamma rays, high-energy electrons, and energetic protons to the lethal mix. No shielding made of matter could meaningfully attenuate it. The radiation passes through kilometers of solid rock without significant attenuation. At closer ranges, within a few light-years of the event horizon, the gravitational gradient, the tidal force, would begin to be significant for extended objects. Tidal forces are differences in gravitational pull across the extent of a body. The pull on one side is stronger than the pull on the other, producing a stretching force along the radial direction and a compression in the transverse directions. At distance, those forces are small. At close range to an ultramassive black hole, they grow. For objects of stellar scale approaching within a few hundred astronomical units of the event horizon, the tidal forces would exceed the material strength of any known substance. Solid rock would deform. Stars would be stretched. The technical term for this process, when it happens to a whole star, is tidal disruption. The colloquial description is spaghettification. For an individual human being, the scale at which tidal forces become lethal would depend on the specifics of the trajectory. For freefall directly toward the event horizon, the tidal force grows as 1 over the cube of the distance. For a human body, the differential gravitational pull across the body's roughly 2-meter extent would become physiologically significant, able to damage tissue and fracture bone, at distances somewhat inside the event horizon radius itself, which means, counterintuitively, that a person falling into a black hole as massive as TON 618's primary would cross the event horizon before being destroyed by tidal forces. The event horizon's radius is so large that the space-time curvature there is relatively mild. You would cross the event horizon and not feel it happen. There is no surface, no wall, no visible boundary, just a region of space that you entered and from which you cannot now escape. The universe behind you has closed off permanently. You are falling, and the fall is permanent, and ahead of you, in the direction of the singularity, the gravity gradient will eventually reach the tidal force threshold, and the physical process of your dissolution will begin. But at the moment of crossing the event horizon, if you could somehow survive the radiation and the long journey to get there, you would not notice anything. You would be inside the largest known black hole in the observable universe, and the experience would feel for a moment like being in empty space. And then, in the hours that followed as you fell deeper, and the gradient steepened and the tidal forces exceeded what matter can withstand, the experience would stop being anything a brain could process. The information about what happened to you, encoded in your physical structure, would be preserved by some interpretations of quantum mechanics in the quantum state of the Hawking radiation, eventually emitted by the black hole over incomprehensible timescales. You would become in a sense part of TON 618. Incorporated into the mass, the information, the quantum state of an object that will persist for longer than the current age of the universe, radiating slowly, the faintest possible glow. A contribution to the most extreme object in the observable universe. This is not reassuring, but it is, in a specific physics sense, accurate. Part 13. The instruments that will change everything. The story of what we know about TON 614 is also the story of what we could not know before the instruments that revealed it were built. And the story of what we will know in the next 20 years is largely the story of the instruments currently under construction or development. Instruments that will make Webb's current capabilities look as limited relative to what they can achieve, as ground-based pre-Hubble telescopes looked relative to Webb. The extremely large telescope, the ELT, is currently under construction at Cerro Armazones in Chile at an altitude of over 3,000 meters, in one of the driest and most transparent atmospheres on Earth. Its primary mirror will be 39 meters in diameter, more than 4 times the diameter of the very large telescope it joins on the nearby plateau. The ELT will be equipped with adaptive optics systems capable of correcting for atmospheric turbulence in real time at a level that approaches the diffraction limit of the telescope, the fundamental resolution limit set by the physics of light, rather than by the imperfections of the observing environment. At that resolution, at the infrared wavelengths where TON 618's host galaxy emission peaks, the ELT will be able to resolve spatial structure at the scale of individual star-forming regions in the host galaxy, not just the integrated light of the whole system. The ELT will look at the TON 618 field and see things Webb cannot see. It will resolve structure in the host galaxy that Webb detects only as a smooth profile. It will separate the primary and secondary sources at spatial scales that clarify whether they are truly distinct objects or an unresolved blend. It will measure the velocity fields of gas in the system in enough detail to constrain the dynamical masses of both central objects independently. The Square Kilometre Array, the SKA, is a radio telescope spread across 2 continents, with collecting stations in South Africa and Australia, connected by high-speed data links to a central processing system in Europe. When complete, it will have an effective collecting area of approximately 1 square kilometre, making it orders of magnitude more sensitive to radio frequency emission than any existing array. The SKA will be sensitive to the synchrotron radiation from the jets of ultramassive active black holes at cosmological distances. It will detect the radio counterparts of the gravitational wave background sources, constraining the orbital parameters and merger rates of the population. And it will, in the pulsar timing mode that detected the gravitational wave background, achieve sensitivity improvements that begin to resolve individual source contributions to the background, not just the overall signal. LISA, the Laser Interferometer Space Antenna, is a space-based gravitational wave detector approved by the European Space Agency for launch in the early 2030s. 3 spacecraft forming an equilateral triangle with arm lengths of 2.5 million kilometers, tracking laser beams between them to detect the minute oscillations in spacetime caused by passing gravitational waves at millihertz frequencies. That frequency range, thousandths of a cycle per second, between the nanohertz range of pulsar timing arrays and the kilohertz range of ground-based detectors, is exactly where the gravitational waves from inspiraling massive binary black holes are expected to fall during the years to decades before merger. LISA will hear individual binary black hole systems, not the integrated hum of millions of them added together. Individual systems, individual mergers. It will detect the chirp signal, the increasing frequency and amplitude of ultramassive binaries in their final approach. For systems at the mass and distance of the proposed TON 614 binary, LISA's sensitivity may not be sufficient for a clean detection. But for systems in the mass range of ordinary supermassive binary black holes at more modest distances, LISA will compile a catalogue that, combined with electromagnetic observations from the ELT and the SKA, will map the population of binary massive black holes across the observable universe. That map will tell us whether the TON 618 system is as anomalous as it appears, or whether it is simply the loudest member of a population whose full extent we are only beginning to characterize. The answer, based on the direction the data has been moving with every instrument upgrade, is almost certainly the latter. But the full picture, when it arrives, will be more detailed than anything we can currently describe. Part 14. The message in the ancient light. Every moment that a telescope is pointed at the coordinates of TON 618, photons completing a 10 billion year journey arrive and convert themselves into electrons in a detector and numbers in a data file. Each photon carries the imprint of the conditions at its source in the early universe, the spectrum of its energy, the polarization of its electromagnetic wave, the timing of its arrival relative to other photons from the same source. All of that information was encoded at the moment of emission and has been carried faithfully across 10 billion years of expanding space, arriving intact, ready to be decoded. The photons do not know they are ancient. They do not experience time. A photon emitted 10 billion years ago and a photon emitted 10 seconds ago are identical quantum objects subject to identical physics. But epistemically, philosophically, in terms of what they tell us, they are very different. The 10 billion-year-old photon carries information about a state of the universe that no longer exists in the form it had when the photon departed. The source has evolved. The host galaxy has aged or merged with something or been disrupted or quietly continued to evolve in ways we cannot see. The binary companion, if it exists, has spiraled closer to merger or has already merged, and the post-merger black hole is now quiet, dark, massive, and unreachable to any observation we will ever be able to make. The photons arriving tonight are the last census we will ever take of that system as it was in the early universe, not the last census of what it has become, the last census of what it was. And what it was, at the moment those photons left, was something we do not yet fully understand, something that does not fit cleanly in our models, something that requires new physics or modified physics or more complete physics to explain. Something that is, as of the most recent reclassification, more complex, more extreme, more embedded in an impossible context than even the already impossible description we had before the Webb data came in. The photons are saying something, the same thing they have always been saying, getting louder and more detailed with every better instrument we point at them. They are saying, the model is incomplete. They are saying, the early universe was more extreme than you thought. They are saying, the most massive things you have found are not the edges of what was made. They are saying, you are still, after 70 years of pointing instruments at us, still learning to read the message we have been carrying since before your solar system existed. Part 15, the payoff, and what worse actually means. Here is the answer to the question the title asked. Is the reclassification reason for alarm? Is TON 618, revised and recontextualized, something that should change how we move through our day-to-day lives? No. The physics of danger over cosmological distances is unambiguous. The revised TON 618 system, one black hole or 266 billion solar masses or 90 billion, solitary quasar or binary immutable Horinsperal, is over 10 billion light-years away. The gravitational influence of even 100 billion solar masses falls as the inverse square of distance, and at that distance it exerts a force on the Earth that is not merely small but unmeasurably, incomprehensibly negligible. Not small in the way that a distant thunderstorm is small, audible, visible, present. Small in the way that a grain of sand is small to the diameter of the observable universe. The radiation from the quasar, blazing at 140 trillion solar luminosities, or more, if the binary feed's combined accretion system, has been travelling toward Earth for 10 billion years and will continue arriving for as long as we point instruments at it. By the time it crosses 10 billion light-years of space, the flux density at Earth is so minuscule that it is detectable only because our instruments are exquisitely sensitive. It is not a radiation hazard. It is not warming the planet. It is not affecting atmospheric chemistry. It arrives, it registers, it is recorded. That is all. The gravitational wave signal from the merger, if it has occurred, passed through Earth at the speed of light and left no measurable trace. The waves stretch and compress the space between atoms by distances smaller than a proton. Nothing detectable by biology, nothing detectable by current technology, nothing that leaves any imprint on the physical world. You are safe. The universe's most extreme known phenomenon is the universe's most remote known phenomenon, and the two facts are not unrelated. But, and this is where 66 billion times worse actually lives, 66 billion times worse is not about danger, it is about understanding. Or rather, about the systematic and deepening revelation that our understanding is wrong in a fundamental way that keeps getting more fundamental with every new piece of data. We were looking at the most famous, most studied, most extreme single object in the observable universe. We had been studying it for 70 years with the best instruments we had. We had produced a description of it that was, by the standards of extreme object astrophysics, thorough and well characterized. 66 billion solar masses, quasar luminosity, event horizon radius, formation paradox, with 3 candidate solutions, all unproven, filed under known unknowns. We thought we had its shape. The reclassification says we did not have its shape. We had one component of it. The other component, the secondary black hole, was hiding behind the glare of the primary, invisible to every instrument we had pointed at it for 70 years, waiting for the right eye to see it. The host galaxy, the context in which TON 618 exists, was more massive than the models assumed, by a margin large enough to move it into a different category of early universe object. The surrounding structure was more overdense than expected. The system was more embedded in impossibility, more surrounded by violations of the standard model's predictions than the already impossible single-object version suggested. We were wrong about the most extreme object we had ever found, not by a little. In almost every important respect, that is 66 billion times worse. Not a threat, a realization. The realization that the edge of our understanding, the place where the most extreme thing we have found lives, is not where we thought it was. That the object we thought represented the maximum extent of what the universe could build, the ceiling of mass and luminosity and impossibility, is a flaw, that there is more. That the early universe was building at scales we have not yet fully characterized. That the pattern of anomalous early massive objects is not a collection of outliers but a statistical population, that our model systematically underpredicts at every mass scale and every cosmic epoch where Webb has looked. The reclassification of Tion 618 is a window opening onto a deeper room, and the deeper room is larger than the room we were in. Part 16. A floor with no bottom in sight. There is a form of discovery that feels like progress and also, unavoidably, feels like the recognition that you are smaller than you thought. Not in size, in comprehension, in the gap between what you know and what there is to know. Every generation of astronomers has believed, and has been wrong, that it was close to a complete picture. Newton believed celestial mechanics was nearly understood. Astronomers at the turn of the 20th century believed the universe was a single island of stars, the Milky Way, surrounded by empty space. In 1920, the great debate over whether the spiral nebulae were nearby gas clouds or distant galaxies had not yet been resolved by the data, and the consensus leaned toward nearby gas clouds. The answer, confirmed by Hubble in the 1920s, was distant galaxies. Billions of them, the Milky Way merely one among an uncountable multitude. The scale of the universe expanded by a factor of billions in a decade. Each revision of scale has made the previous picture look not just incomplete but provincial. Parochial in a way that is, in retrospect, almost charming. The certainty with which wrong views were held. The comfort with which a too small universe was described as if it were the full and final thing. We are not immune. We are not special. We are not the generation that finally has the right picture in full. The history of astronomy says we are the generation that has the current picture, which is better than all previous pictures, which will look to future generations the way past pictures look to us. Correct in the regions where we tested it, provincial in the regions we could not yet see, confident in a scale that turned out to be smaller than reality. Ton 618's reclassification is, in that arc, exactly what you would expect. The most extreme thing we found turned out to be more extreme when we looked harder. The context around it turned out to be more impossible when we measured it better. The implications of its existence turned out to be more structurally significant for our cosmological models when we took the full picture seriously. And when Lisa launches and begins listening to the gravitational wave sky, when the ELT begins resolving the structural details of early universe-host galaxies at spatial scales that are currently impossible, when the SKA begins mapping the radio universe with sensitivity that dwarfs everything before it, the picture will expand again. The extreme will move further out. The anomalies will multiply into a clearer pattern. The new physics required to explain the pattern will become more constrained and eventually more visible. We will not find the edge. The history of cosmology suggests there is no edge to find. Just a horizon, which recedes as you walk toward it, always keeping the same apparent distance, always revealing a little more of the territory you are crossing. The territory is larger than the map. It always has been. Part 17. The patience of the signal. There is one more thing worth sitting with before we end. The system at Ton 618, whatever it actually is, one black hole or two, blazing quasar or partially obscured binary, impossible galaxy or more impossible galaxy, has been sending its light toward us since the universe was 3.5 billion years old. For over 10 billion years, that light has been traveling through space that was expanding around it, through gravitational fields that bent its path, through gas clouds that absorbed most of it and transmitted a thin fraction, aimed at a patch of expanding space that would eventually, after the formation of a second generation of stars and a solar system and a rocky planet and multicellular life and technological civilization, contain instruments capable of receiving it. The light did not aim itself. Photons do not aim. They travelled in all directions from their source, and the ones that happened to be aimed in this direction have been travelling for 10 billion years, and they are arriving now. The signal has been patient in the only way physical processes can be patient, by simply continuing to travel, continuing to carry its encoded information about a system in the early universe through the expanding dark between then and now. And the information it carries, decoded by Webb's infrared detectors, and the spectroscopic pipelines, and the modelling teams who fit galactic mass profiles to the light distribution, and the dynamical teams who constrain the mass of any central black hole from the orbital velocities of surrounding stars and gas. That decoded information says, in the language of astrophysics, this system is more than you thought. It is more complex, more massive, more embedded in an impossible structure, more resistant to explanation by your current models, and more representative of a broader pattern in the early universe than you realized when you first catalogued it 68 years ago on a photographic plate in Mexico. You were right to keep looking. You were right to build better instruments. You were right to take the anomalies seriously rather than explaining them away. The universe rewards that. Not with comfort, not with closure, with more data, with better defined questions, with a clearer map of the territory you do not yet understand. Somewhere, in the data that has already been collected, in the archives of Webb and the pipelines of the pulsar timing arrays and the photometric catalogues of every deep field survey ever done, there are more TON 618s waiting. More objects whose classification will change when the right analysis is applied. More second sources hiding behind glare. More host galaxies whose masses are underestimated. More binary systems whose companions have not yet been resolved. More patterns in the distribution of early massive objects that will, when they finally become visible, force another round of revisions to the standard model. The data is patient too. It waits in servers. It waits for better algorithms. It waits for researchers who have not yet been trained to ask the right question of it. It waits for the next generation to come along and notice what this generation has missed. TON 618 was on a photographic plate for 15 years before anyone understood what it was. The second source at TON 618's redshift was in the photon field for 70 years before Webb's infrared eye resolved it. What is currently hiding in plain sight, in data we already have, in archived observations we have already made, in signals we have already recorded and not yet fully analyzed? We do not know. We will find out. And when we do, the picture will be larger than this one. It always is. Stay curious. Stay unsatisfied. And the next time someone tells you the universe is mostly understood, remember TON 618. Remember that the most extreme object we had ever found was hiding a companion. Remember that its galaxy was 70% more massive than our model said. Remember that it sat at the center of a cosmic web overdensity we had underestimated. Remember that the universe does not reveal itself in a single revelation. It reveals itself in layers, each one built on the last, each one showing more than the one before, each one showing how much the one before was missing. We are in the layers. We are not at the bottom. There is no bottom in sight. Thanks for watching. I'll see you in the next one.